Golden Iris Production presents From Coulomb's Law to the Planck Length by Mark F. Dennis. Abstract. Beginning with Coulomb's law, we express the electromagnetic constant in progressively deeper forms. By substituting identities linking epsilon naught, mu naught, c, h bar and g, we arrive at the Planck length. The result reveals how electromagnetism, relativity, quantum mechanics and gravity intersect at a single natural scale.
Coulomb's constant. Coulomb's constant defines electrostatic strength. K equals 1 over 4 pi epsilon naught. K equals 8.987551788 times 10 to the 9th. 4 pi epsilon naught equals 3.89428 times 10 to the minus 10, including charge. Introducing the elementary charge Q. 4 pi epsilon naught divided by Q squared equals 4.33449 times 10 to the 27. The scale now depends on charge structure.
Substituting vacuum identity. Using the identity epsilon naught equals 1 over mu naught c squared, we obtain 4 pi divided by mu naught c squared q squared equals 4.33449 times 10 to the 27. Electromagnetism now links to relativity. Rearranging in terms of c. Rewriting the expression 4 pi c squared divided by mu naught q squared equals 3.50123 times 10 to the 61. The scale increases dramatically.
Expressing via epsilon naught mu naught. Since c squared equals 1 over epsilon naught mu naught, we rewrite as 4 pi divided by epsilon naught mu naught squared q squared equals 3.50123 times 10 to the 61. Now geometry begins to appear. Introducing the Planck length. Define L sub p squared equals h bar g divided by c cubed. Substituting gives 4 pi L sub p squared divided by epsilon naught mu naught squared q squared equals 9.14619 times 10 to the minus 9. Quantum gravity enters the structure. Recovering g. Rearranging yields g equals L sub p squared c cubed divided by h bar. G equals 6.6743 times 10 to the minus 11. The gravitational constant emerges naturally. The Planck length. Finally, L sub p equals square root of h bar g divided by c cubed. L sub p equals 1.61626 times 10 to the minus 35 meters. This is the natural length scale where quantum mechanics and gravity meet.
What is the Planck length? L sub p equals 1.61626 times 10 to the minus 35 meters. The Planck length is the unique natural scale constructed from h bar, g and c. It does not arise from measurement alone, but from dimensional necessity. When quantum action, gravitational curvature and relativistic structure are combined, a single fundamental length emerges. Physical meaning. L sub p equals square root of h bar g divided by c cubed. H bar governs quantum discreteness, g governs space-time curvature, c governs causal structure. At the Planck scale, these three domains are no longer separable. Quantum mechanics and gravitation converge into a single regime, where classical space-time description fails. Geometric interpretation. Below the Planck length, the concept of distance loses operational meaning. Any attempt to localize a region of space to scales smaller than L sub p introduces gravitational effects strong enough to disturb the geometry itself. The Planck length therefore marks the boundary at which quantum gravity becomes unavoidable. Equivalence via alpha and vacuum structure. Starting with G equals L sub p squared c cubed divided by h bar, using the identities alpha equals q squared divided by 4 pi epsilon naught h bar c and c squared equals 1 over epsilon naught mu naught. Substituting for h bar and c to the fourth reduces the expression to G equals 4 pi L sub p squared alpha divided by epsilon naught mu naught squared q squared. Relating the two scales. Part 1. Preon scale. R sub 0 equals L sub p times square root of alpha. Classical electron radius. R sub e equals alpha times lambda sub c, where lambda sub c equals h bar divided by m sub ec. Taking the ratio, r sub 0 divided by r sub e equals L sub p divided by lambda sub c times 1 over square root of alpha. Relating the two scales. Part 2. R sub 0 equals 1.3805 times 10 to the minus 36 meters. L sub p divided by lambda sub c equals 4.187 times 10 to the minus 23. 1 over square root of alpha equals 11.706. The ratio r sub 0 over r sub e equals 4.90 times 10 to the minus 22. Solving for r sub e equals r sub 0 divided by 4.90 times 10 to the minus 22 equals 2.81794 times 10 to the minus 15 meters. Geometric relationship to the electron radius. The quantity L sub p squared times alpha represents a geometric electromagnetic area scale formed by weighting the Planck area with the fine structure constant. Taking its square root produces L sub p times square root of alpha, a length that lies between pure Planck geometry and classical electromagnetic structure. Through the reduced Compton wavelength, lambda sub c equals h bar divided by m sub ec, this intermediate scale connects directly to the classical electron radius. R sub e equals alpha times lambda sub c. The electron radius therefore emerges as the Compton scale amplified by alpha, while L sub p times square root of alpha appears as its deeply suppressed geometric precursor. Classical electron radius. The classical electron radius is defined by R sub e equals alpha times h bar divided by m sub ec, using alpha equals 7.29735 times 10 to the minus 3, and h bar divided by m sub ec equals 3.86159 times 10 to the minus 13 meters, gives R sub e equals 2.81794 times 10 to the minus 15 meters. Classical and Schwarzschild radii. The classical electron radius arises from equating the electrostatic self-energy of a charged sphere with the electron rest mass energy. It represents an electromagnetic length scale derived from alpha, h bar, and me. By contrast, the Schwarzschild radius, Rs equals 2gme divided by c squared, is the gravitational radius associated with the same mass. For the electron, Rs approximately 1.35 times 10 to the minus 57 meters, more than 40 orders of magnitude smaller than Re. This enormous separation reflects the relative weakness of gravity compared to electromagnetism at particle scales. Emergence of the classical electron radius. Equate electrostatic self-energy to rest energy. Kq squared divided by r equals m sub e c squared. Solving for r
R equals kq squared divided by m sub e c squared equals q squared divided by 4 pi epsilon naught m sub e c squared. R sub e equals 2.81794 times 10 to the minus 15 meters.
From Coulomb to the Planck scale. We began with Coulomb's law, expressing electric interaction through Q and epsilon naught. Rewriting alpha and using c squared equals 1 over epsilon naught mu naught allows the gravitational constant to be written as g equals L sub p squared c cubed divided by h bar. In this form, gravity appears as a geometric consequence of quantum structure, and the Planck length emerges as the fundamental gravitational scale. From the Planck scale to the electron. Multiplying L sub p squared by alpha produces a smaller geometric scale. Its square root, r sub 0, equals L sub p square root alpha. Through the reduced Compton wavelength, lambda sub c equals h bar divided by m sub ec, this connects to the classical electron radius, r sub e equals alpha h bar divided by m sub ec. Thus, electromagnetic structure links quantum geometry to the observed size scale of the electron.
From the electron to black holes, gravity defines the Schwarzschild radius. R sub s equals 2gm divided by c squared. For the electron, this radius is unimaginably small. For stellar masses, it defines black holes. Together, these relations trace a continuous ladder from charge to quantum length to gravitational curvature. Classical electron radius versus Schwarzschild radius. Electromagnetic self-energy scale. Re equals kq squared mec squared equals q squared 4 pi epsilon naught mec squared. Gravitational curvature scale. Rs equals 2gm divided by c squared. Both radii arise by equating an interaction energy to the rest energy scale, mc squared. The classical radius depends on charge and epsilon naught, while the Schwarzschild radius depends on mass and g. They share the same relativistic normalization factor, 1 over c squared.
Structural analogy, gravity and electromagnetism. Gravitational collapse defines the Schwarzschild radius. R sub s equals 2gm divided by c squared. This radius is obtained by equating gravitational interaction energy to the relativistic rest energy scale. Electromagnetic self-energy defines the classical electron radius. R sub e equals kq squared divided by m sub e c squared. This is equal to q squared divided by 4 pi epsilon naught m sub e c squared. This radius is found by equating electrostatic self-energy to m sub e c squared. Both radii share the same underlying structure. Characteristic length equals interaction strength divided by c squared. Charge as a source of curvature. In general relativity, space-time curvature is sourced not only by mass, but by the full stress energy tensor. The electromagnetic field carries an energy density. U equals epsilon naught E squared divided by 2. This energy contributes to space-time curvature through Einstein's field equations. Thus, electric charge, through its field energy, participates in shaping space-time geometry.
Electromagnetic contribution to time structure. Space-time curvature modifies the metric component g sub tt. This component determines gravitational time dilation. Because electromagnetic fields contribute to the stress-energy tensor, they alter the time structure of space-time. Charge therefore generates a time gradient, just as mass does. However, the radial dependence is different, and the magnitude is typically much smaller.
The charged metric. The Reissner-Nordström metric, g sub tt equals 1 minus 2gm divided by rc squared plus gkq squared divided by r squared c to the fourth.
The mass term scales as 1 over r. The charge term scales as 1 over r squared.
Atomic structure and scale separation. Although electromagnetic energy contributes to curvature, its geometric effect at atomic scales is extraordinarily small. The stability of electron orbitals in hydrogen and in all atoms arises from quantum mechanics and the Coulomb potential. It does not arise from space-time trapping. Nevertheless, the presence of charge in the stress-energy tensor shows that both mass and charge participate in the geometric structure of space-time. What we learned: structural parallels. We began with Coulomb's law and the fine structure constant. This revealed that gravitational structure can be written in the quantum form: G equals L sub p squared c cubed divided by h bar. From this expression, the Planck length emerges as the fundamental gravitational scale. Multiplying L sub p squared by the fine structure constant alpha introduces a smaller geometric scale. The square root of this scale connects, through the Compton wavelength, to the classical electron radius. R sub e equals q squared divided by 4 pi epsilon naught m sub e c squared. Across scales, characteristic radii arise when interaction energy reaches the relativistic energy scale, mc squared.
From charge to curvature. Both mass and charge contribute to space-time geometry through the stress-energy tensor. Gravity defines the Schwarzschild radius. R sub s equals 2gm divided by c squared. Electromagnetism defines the classical electron radius through self-energy balance. Although these scales differ enormously, they reflect the same structural principle. Interaction strength divided by the relativistic energy scale c squared produces a characteristic length. From quantum charge to black hole curvature, geometry emerges from energy.
A thread through the constants. From Coulomb's constant to the Planck length. From the Compton wavelength to the electron radius. From charge energy to space-time curvature. We followed a single idea. Energy defines geometry. Across scales, interaction strength normalized by c squared produces structure. The question that remains: if mass shapes space-time, and charge carries energy, and energy curves geometry, what else is encoded in the constants we have treated as fundamental? The journey is not finished. To be continued.